Bismillahirrahmanirrahim. Let's go over the process of state feedback controller and observer design. So we went over the process of controller and observer design, and we discussed the pole placement method for the controller and observer design. And for the control design, what you need to do is decide the location of poles and uh, decide the location of pole of controller observer pole and second require calculate the required or desired characteristic equation from the suppose the pole are at minus alpha and minus beta, and then required characteristic equation will be like this: s plus alpha s plus beta equal to 0. So we'll decide the location of the pole of the observer and controller based upon the required agility of the system. And remember the important point over here that observer pole will be much faster compared to the controller pole. Otherwise, observer will not be able to catch up with the system if there is a reference input to the system. So observer should be much faster than the controller. So using the location of the pole, you'll decide the uh, desired characteristic equation, and then you'll just compare this equation to uh, for controller. For controller, you'll compare this equation, desired characteristic equation, to this equation, Si minus A minus Bk mod equal to 0. And here you what you don't know is the value of k, k1, k2, k3, and k will have the same entities as the number of states. And for control for observer, you compare this desired characteristic equation to the observer characteristic equation, which is Si minus A minus Lc. And here this is the characteristic equation, and L1, L2, L3 will be the unknown. Actually, this is the equation of error, not the whole observer, but normally it is called the observer characteristic equation. But the truth is, truth is uh, that in the exact sense, this is the dynamic equation for the error, and we want to converge that error to 0, so we'll just make this system stable. And remember that if you are not given the desired location of the poles of the observer, you need to select, you have the freedom to choose the desired characteristic equation of the observer depending upon the required location of uh, system poles. System poles are at A minus BK, and observer should be 10 times faster. So you are not given the uh, if you are not given the agility of the observer, you have the freedom to select the observer poles. And remember, observer poles should be ideally 10 times faster than the controller poles, right? And there is another way to do that. This is done by comparison, comparing the coefficient of this equation with this, or this equation with this, depending upon whatever you want to design the observer controller. And there is another method, and you can rather than solving the simultaneous equation, you can calculate the gains directly for controller. You can go there is a formula which is called Ackermann's formula: Ackermann. Ackermann's formula. And Ackermann's formula for a controller K. K is 0, 0, 0, and last entity will be 1. And P, C inverse. And here you have Q and A. Now this is all all zero entries except the last entry will be 1. This vector, this is control inverse of controllability matrix. And what is this QA? QA is the correct desired characteristic equation with S replaced by A. So if I calculate the characteristic equation for this system, suppose this is the system. So the characteristic equation will be S square plus alpha plus beta S plus